Hello, Mr. Kaladi here, and today we are going to start the second chapter of calculus, second subchapter, which is all about derivatives. Now, if the first subchapter, limits, that's the why calculus works. That's the background of the secant and tangent lines and limits, first principles. Now, in the derivatives chapter, this is really the how of calculus. How we actually find slope of tangent of really difficult functions. So let's go back to what is calculus again. Calculus is finding the slope of a curve or the slope of the tangent line. And when we finished our last subchapter, we had an equation. The slope of the tangent line is equal to the limit as h approaches 0 of f at x plus h minus f at x over h. This was called first principles. So as of today, from now on, we're no longer going to call this first principles m tangent. We're going to call it the derivative. We write it as f prime at x is equal to the limit h approaches 0 of f at x plus h minus f at x over h. So what is this? This is the derivative. So when I say derivative with this notation, f prime at x, I really am saying slope of the tangent. This is just the big kid way of saying it. Now there's a few different ways we write the derivative. So we have f prime at x. I'm just going to tell you how to pronounce it. So it's f prime at x. We might just write it as y prime. Or another common one is dy dx. dy dx. We also have a few other ones. These aren't as common, but we have d dx of f at x, big D x of y, and d f at x. But those are not as common. So these are all ways of writing the derivative. And what is the derivative again? It's a nice name that means slope of the tangent. Okay, so what is the derivative really? Well, remember, that was from that previous lesson. If I have any curve and I want to find out the slope at a certain x value, I would draw a tangent line. The slope of that tangent line, is the slope at that point, that instantaneous point. So instead of saying slope of the tangent line, we're just going to say derivative. So the derivative at x equals a is the slope at x equals a. So let's write that out. What is the derivative really? It is the slope, or I think I already introduced this, the word gradient is a nice way of saying slope. Oh, it's another way of saying slope that they use in IB. So the derivative is the slope of the tangent line at a point on the curve. Another way of looking at it, the derivative is the instantaneous rate of change. Remember, we kind of introduced this, we introduced the idea of rate of change in our last little subchapter. The rate of change is another way of saying slope, is another way of saying gradient, another way of saying now derivative. One question we looked at, we were looking at bacteria per hour. Right, so that's the instantaneous rate of change. And another way of looking at this is, and if you want to look at dy dx, resembles delta y, delta x. So we would say that this is the derivative of y with respect to x. Right? These kind of resemble each other, dy dx. Now, for now, we're going to say dy dx, this is a notation. It's not really a fraction. Not really, not right now at least. It's just a way of writing the derivative. But it kind of does resemble this slope formula, and that's sort of all related, right? Because that's what this is. This rate of change is a slope. Okay, and now maybe you understand this joke. So the derivative of Optimus with respect to x, just like the derivative of y with respect to x, we might just call it y prime. So this would be derivative of Optimus with respect to x is Optimus prime. Aha, great joke. Okay, now that's the derivative on all our different notations. So this is great. Derivative, if I ever wanted to find it out, it's just the limit as h approaches 0, f at x plus h minus f at x over h. The one thing that we hate about first principles is it takes forever. Now, fortunately, you know how to do it. You have to do one question on the test and exam. But we're going to teach you I promised we'd teach you a shortcut, and that's what today's all about. So we're no longer going to be using this. It was useful. It's the foundation of calculus, so we can always go back to it if we're ever unsure, and hopefully we understand where it comes from. But now we're going to leave it behind, and we're going to develop some rules for differentiation. So again, develop rules. We're really going to develop some shortcuts. And differentiation, well, that word means the process of finding the derivative. Okay, so here we go. Let's start with our first rule. And there's going to be a bunch of them over the next few weeks, I guess. The first one, the constant rule. If f at x is equal to c, then the derivative, f prime at x, is equal to 0. Is that okay with everyone? Okay, you should be saying, no, that's not okay. I want some proof. I don't just believe you because you write something on a printed piece of paper. Okay, you should be saying, I want to see proof. And so let's show you some proof, because all of our rules can be proved with first principles. So remember first principles, we have to declare f at x, which in this case is c, a constant, and f at x plus h. So if I add h to all the x's, this is still a constant. So now, first principles, I use my derivative formula. So it's the limit as h approaches 0 of f at x plus h minus f at x over h. I sub in my values. I get the limit as h approaches 0. Okay, so I'm going to sub in c minus c over h. So I end up with the limit as h approaches 0 of 0, which is just 0. So there you have it. The proof is always in the foundation of calculus, which is that first principles. And indeed, the derivative of a constant is 0. So if I ask you, if you have a function that's f at x equals 5, the derivative of it is 0. Man, that was very quick. Just to kind of illustrate this point, I want you to think just a second. Like, think about what this graphically looks like. F at x equals 5 is just a horizontal line, right? F at x equals 5 is a flat line. So if I ask you for the derivative, well, remember, derivative just means slope. What's the slope of a flat line? The slope of the line is 0. So it makes sense that the derivative is 0. And graphically, these two things will really kind of prove it. But for now, we just have to know how to deal with it. So again, I have another equation, y equals 7. The derivative, I can write it a different way. This is another, get used to that form, notation. It's 0. Y equals pi. Y prime is equal to 0. Because pi is just 3.14, so it's just a constant. So that's our first rule, the constant rule. That's a nice one. Let's turn the page. Let's do the power rule. Now, power rule, starting to get more complicated. If f at x is equal to x to the power of n, then the derivative is n, which is the exponent, times x to the power of n minus 1. So if I had x squared, well, the 2 would come down here, and then the exponent would change to 2 minus 1, which is just 1. I know you're saying, oh, sir, I want to see proof. Again, you can Google proof. Here I have, like, I always show, I scanned in from old textbooks some of the proofs. So they have a long proof. It's much more difficult than the last one. But needless to say, all of this is still based on first principles. So if you're really interested, all of these rules, if you want to look, you can look, ask me for the proofs, or you can just look online. Or don't worry about it. Okay, but never believe what people tell you unless you see proof. Okay, so here we go. Let's apply the power rule. Here's my function. What's my derivative? Well, I bring the 2 down, so the exponent comes down, and then the exponent I subtract 1. So I end up, well, I'm going to write out the step, but you don't have to write out this step every time. 2x. Does that number look familiar? Hopefully. And I don't think I have my sheet with me. Hopefully it looks familiar, because that is the same as when we did it by hand, right? We did x squared by hand in first principles. It gave us 2x. But now, like I told you, you don't have to do this. You can do it in like 10 seconds. X squared, you just bring the 2 down, subtract 1 from the exponent, and you get 2x. Very easy. Let's do some more complicated questions. This one, y equals x to negative 4. Well, y prime is equal to, okay, bring the negative 4 down, then I subtract 1 from the exponent. So that gives me negative 4 to the x minus 5. I don't like negative exponents in my final answer, so I'm going to write negative 4 over x5. Okay, this next question, very similar to the other ones, but just the notation is a little different. The dy, this is an operator that says, actually this is the operator, dy dx, not dx. This essentially says to us, find the derivative So this question is saying, find the derivative of x. So in that case, the derivative of x is just, well, okay, bring the 1 down, and I take 1, subtract 1. So I end up with 1 times x to the 0, which is just 1. The difference is that this is like an equation where this is just an operator. So it's telling you find the derivative of this, and you say, okay, well, I can find the derivative of this, and you do it. Okay, let's do this next question. First of all, I don't like square roots, so I'm going to rewrite this as x to the half. Okay, let's find dy dx, or in other words, the derivative. So I bring half down, then I take my exponent, and I subtract 1. Now see how it's useful to write the step out? Because now I can be more methodical about my math. It's getting a little difficult. This is actually x to the half minus 2 over 2. Right? We want a common denominator if we're going to subtract. So then I end up with 1 over 2 x to the negative half. And again, I don't like negative exponents, so I'm going to have 1 over 2 x to the half, or 1 over 2 root x. And I would say either is fine. Okay, next question. Now, have I taught you how to take the derivative of two functions multiplied together? No, unfortunately we have not learned this yet. But I can simplify this to make it look like this, 1 power. And to do that, you're going to use your exponent laws. So I have x to the power of 1 times x to the half. That is x to the 1 plus half, which is x to the 3 over 2. Now, if I want to take the derivative of that, it's 3 over 2, x to the 3 over 2 minus 2 over 2. That gives me 3 over 2 x to the half. Finally, this question, again, I haven't really taught you how to deal with this, but if you rewrite it as a negative exponent, well, now it looks like this rule up here, and I can use my derivative trick, my power rule. So this is negative 7 over 3 x to the negative 7 over 3 minus 3 over 3. That gives me negative 7 over 3 x to the negative 10 over 3. And let's just clean that up a bit. Negative 7 over 3 x to the 10 over 3. So see how you can get a little quicker, but it still is sometimes really useful to write out a little bit more work. Like maybe in this one you could jump right here. But once you start getting rational expressions like fractions, it's useful to show your steps because you might lose something. So we've learned the constant rule, the power rule. Let's do rule number 3, constant multiple rule. Isn't this fun? If y equals a constant times a function, then the derivative is the constant times the derivative of the function. So it's almost like the constant, the derivative passes through the constant and just goes after the function. So let's do an example. Again, if you want to see proof, you can find the proof online. What is the derivative of 3x to the power 4? Well, we just learned the 3 we don't care about. We pass through the 3, and now we just need to know the derivative of x to the power 4. Well, the derivative of x to the power 4 is 4x to the power of 3 using my power rule from above. So my final answer is 12x to the power of 3 because I simplify at the very end. Let's do the second one. The derivative of 8x. Well, ignore the 8. Tell me, what's the derivative of x? Well, x to the power of 1, I bring the 1 down. I subtract 1 from 1. Oh, yes. So I just get 8 times x to the power of 0, so I just get 8. Note this kind of form. Anytime you have a linear equation, you take the derivative, it's always just the constant. And this makes sense, right? The slope of this line, y equals 8x, is 8. So it's kind of like a quick jump you get to do. What about this 6 over x squared? I have not shown you how to solve this, but if you rewrite it like that, well, now this looks a lot like the other questions. dy dx in this case, I ignore the 6. What's the derivative of x to the negative 2? Well, bring the negative 2 down, then I subtract 1 from the exponent, so I have negative 3. Now, let me simplify, I get negative 12x to the negative 3. We don't like the negative exponent. Okay, final rule. Well, there's two rules here, the sum or difference rule. The sum rule means if I have a function which is two functions being added together, the derivative is the derivative of the first function plus the derivative of the second function. You kind of find the derivative separate. And similarly if they're being subtracted. So this means now I can give you a long polynomial, and basically you treat it as 3 mini derivatives. So the derivative of this is 7, okay, times the derivative of x squared, which is 2x to the 1, plus 2 times the derivative of x, which is x, just x to the power 0, plus 4 times the derivative of x to the negative 3, which is negative 3x to the negative 4. Whew. Now all my derivative work is over. Now you could give this to a grade 9 student and they can just simplify it for you, right? This is no longer calculus, this is just algebra. This is going to become 14x. This is going to become 2. This is going to become negative 12x to the negative 4. I like all of this except for the negative exponent. Okay, and one more question. Again, look at all this. There's so many complicated functions here. But again, I'm just going to do one at a time. Well, first I'm going to clean it up a little bit because I can't deal with some of these things. So this is negative 2x to the 4. This is x to the half minus 5 minus 3x to the minus 5 plus 7x to the 4 over 3. Now I take the derivative. So we go y prime is equal to negative 2. Let's deal with this. So that's 4x to the power of 3. Now the derivative of this is half x. I subtract 1 from half, which just gives me negative half. The derivative of a number like 5 is just 0. The derivative of, okay, well, negative 3, then what's the derivative of this? Negative 5x to the negative 6. Plus 7, can we fit it in? 4 over 3 times x. We have to subtract 1 from this. So that's going to become, you know what, I'll show the step. 4 over 3 minus 3 over 3. Just fit it in. Ugh, looks terrible. Okay, now the calculus is over. The rest is just numbers. So this is going to become negative 8x to the 3 plus half x to the negative half plus, so negative times negative is plus 15x to the negative 6. 7 times 4, that gives me 28 over 3. Hope you remember how to multiply fractions like that. And this becomes x to the third. We're almost done. I just want to get rid of the negative exponents. So my final answer is negative 8x cubed plus 1 over 2 x to the half plus 15 over x to the 6 plus 28 over 3 x to the third. Just want to make 2 notes here. So on a Colati style test, avoid negative exponents. In your final answer. And most calculus teachers at this school are like that. On an IB test, you simplify only if necessary. And they'll tell you. But you don't have to worry about cleaning it up so much. Okay, and finally our homework is page 203, number 1 to 6, and 205, number 1 to 15. Good luck, and we'll see you next time.